Welcome, students. Today we are going to discuss weight and weightlessness. We are going to discuss the two with respect to an elevator and also a spaceship. So here is my elevator, and the cable here. These are the walls inside the track of the elevator. So the elevator is basically this one. This is the focus of our elevator. And I'm going to put a scale in the elevator. So there's a giant scale here. So that's a scale. Then I'll put a crate, or a crate of mass 10 kilograms. All right, I think you're able to see the 10 kilograms. This is the scale, and there is a crate of mass 10 kilograms. Now, the force diagram here will help us to understand what's going on here. The force diagram, remember, it shows an object and forces acting on it. So there is mg, the force due to gravity. Sorry. And also in general, there is a support force or the scalar force, because the scale is exerting a force on the mass, but also there is gravitational force pulling it down. So that's the force diagram. In general, we learned that we can apply Newton's second law to understand how the forces behave. So the net force must be equal to mass times acceleration in the y direction. Now, Fs is acting upward, so it'd be plus Fs. And then we have to add mg is acting downward, that's minus mg. The result must be mass times acceleration in the y direction. This gives me support force minus mg equal to mass times acceleration in the y direction. And now I can move this to the right. So the support force, or the scalar force, will be equal to mg plus may. So I transferred this to the right hand side. It will be plus mg. So the support force is actually m. I take out m here, then I have g plus ay. I am just rewriting this equation here so that it's a little bit more nicer. So the support force, or the scalar force, the force that I can read on the scale, is given by m open bracket g plus acceleration in the y direction. This force is what we are going to call the weight of the crate. So weight of the crate is given by Fs. So our weight will be, we define here in this discussion, we define weight as the scalar force on the crate. As the scalar force on the crate. Or you should say that it is actually the force exerted by the scalar on the crate. So this is what we are going to call the weight of the crate. Actually, when you place the crate on the scale and you see that there's a reading on the scale, that reading tells you how much the scale is pushing on the what? It's pushing on the crate, is pressing on the crate. All right, so without this support force, you know that the crate won't be at rest. The support force, or the scalar force, is the one that is balancing the gravitational force if there is no acceleration on the crate. Now, we are going to ask ourselves what will happen to the weight, and the way we have defined it here, what will happen to the weight if acceleration changes. So we are going to try different values of acceleration and see how the weight of the crate will be like. So we are starting. So if acceleration in the y direction is 0 meters per second squared, what is the weight. So weight will be how much? Now remember our equation, we said weight is m times g plus acceleration in the y direction. Our mass in this example was 10 kilograms, and our g is 9.8 meters per second squared. We are adding 0 meters per second squared because acceleration is 0. Please take note that when we say acceleration is 0, there are two possibilities. The crate or the elevator could be at rest, or it could be moving at constant velocity, up or down. So we have two situations here, at rest or moving at constant velocity. So what would be the weight? So in that case, our weight will be 10 kilograms times 9.8 meters per second squared. This gives us 90 what? It gives us 98 newtons. So the weight is 98 newtons. But realize that the weight will be different if we change the acceleration. For example, let's use the different mark. If acceleration in the y direction is, for example, let's say 4 meters per second squared upwards. So plus, so if I say plus, that means upwards. So what will be the weight? If you do the same, weight will be equal to m times g plus acceleration in the y direction. We have your mass as 10 kilograms. G is 9.8 meters per second squared, and the acceleration is 4 meters per second squared. If you solve this one, you should be able to get 138 newtons. So it looks like now the crate will be heavier. The crate will be heavier. If it was a person, the person would be heavier in that situation, because this was the normal situation, at rest situation. And this happens to be when the elevator is accelerating upward, you have a larger weight. And that's what happens when you are in the elevator and you are accelerating upward, you feel heavier. Now, what about if acceleration is downward, minus 4 meters per second squared? What would be the weight? So do the same thing. Weight will be equal to, I'll just plug in the numbers, 10 kilograms, 9.8 meters per second squared, plus minus 4 meters per second squared, close bracket. What will be the result? Now I invite you to use a calculator, do this operation, 9.8 minus 4, then the answer times 10, you're going to get 40, because 9.4 minus 4 is like 5.8 times 10 is 58. Looks like the crate will be lighter, so 58. This is interesting because this is a normal situation. This is kind of heavier, and this is a lighter. So depending on the acceleration, the weight of the crate will be different. Now there is an interesting case whereby acceleration is 9.8 meters per second squared downward. So this means the elevator cable is broken and the crate and everything in the elevator are falling down. They are in free fall. They are falling down at an acceleration rate due to gravity. So this is like free fall case, free fall. So what will be the weight of the crate? We do the same thing. Weight is mass, g plus acceleration in the y direction. Now the mass is 10 kilograms. We have 9.8 meters per second squared. Now plus minus 9.8 meters per second squared. Now realize that the result of doing this will give us a 0. because 9.8 plus minus 9.8 is 0. So 0 times 10, the answer is 0. So we are saying that the weight is 0 newtons. This is very, very interesting. It tells us that the crate is weightless. So the crate is weightless. Let me use a different marker to emphasize the point. So the crate is weightless. It has no weight. The weight is 0. It is weightless. Now, this is actually the case when objects are in free fall. By definition, we say free fall is motion under the influence of gravity only. So if we say the only force is gravity, that makes sense. It means there's no scalar force, there's no support force. And this scalar force is what we define as weight in this discussion. So there's no weight. There is no weight because the crate is in free fall. The only force is gravity. There's no support force. There's no scale force. Even if the crate was resting on the scale won't have a chance to press on the crate because the scale itself is in free fall. I would like you to remember Galileo's experiment where he dropped objects of different masses. He saw that different objects or objects of different masses fall at the same rate. So in this case, what we are seeing here is that there is a situation here whereby the scale, the crate, they are all falling at a rate of 9.8 meters per second squared downward. And therefore, there is no scale force. So the support force is equal to 0. And that's what we call weightless situation. All right, so note that astronauts in an Earth orbiting spaceship are also in free fall, and there is no scale force. Hence, they are weightless. They actually accelerate at the same rate as the spaceship, and the support force is 0. So let me take note of that. So what you are saying is that astronauts in an Earth orbiting spaceship are also in free fall, just like the case of the elevator cable broken, and there is no support force. Hence, they are weightless. So everything in the elevator, the astronaut, whether there's a scale, whether they have some bags, everything in the scale accelerate at the same rate. So the astronauts accelerate at the same rate, as the spaceship itself. Now, I want to warn you guys, if you think about this, you might be mistaken to think that there's no gravitational pull on the astronaut that are orbiting the Earth. You might be mistaken. Realize that the reason the spaceship and the astronaut are orbiting the Earth is because of gravitational pull. And therefore, do not explain weightlessness in this case by saying that there is no gravity on the astronauts. That will be incorrect. That will not be correct. There is actually gravitational pull pulling the astronaut inside the astronaut and the spaceship downward. So there is gravitational pull. There's a spaceship here. There is gravitational pull, but what's absent is the support force. And remember, we said weight is the support force or the scale force. So in this case, there's absence of support force, and therefore the astronaut will be weightless, will have no weight in this case, okay? And the weightlessness is not the absence of gravitational force. It is absence of support force. It is very, very important. So Fs is equal to 0. Weight is equal to 0. And this is a gravitational force.